Hello, good morning, and welcome to lecture number 7 by my count on consensus in distributed systems and blockchain. This is yet another background lecture, right? So I'll be going through different consensus problems and solutions. So consensus has been defined as a classical problem in many settings, long before cryptocurrencies. The first discussion of consensus came up in the context of Byzantine generals, which we saw in the first lecture. This is in 1982, they proved the impossibility when at least 1/3 of the nodes are malicious or Byzantine. In 1985, we had another very fundamental result, the FLP theorem, impossibility in asynchronous systems. I'm going to discuss it soon. In 1989, they came up, Leslie Lampert, who later got the Turing Award, came up with the Paxos protocol. And the Paxos protocol is one of the most common solutions used in the industry, and again, I'm going to discuss it today. However, Paxos came before its time, because in 1989, it was purely theoretical. It was not until 10 years later when Paxos was rediscovered and got into major infrastructures of Google, Oracle, Yahoo, and other companies. In 2006, Google came up with the Chubby service, which is based on consensus. And again, I'm going to talk about it today. 2010, Yahoo Apache Zookeeper came up. 2013, the Raft solution to consensus, which is one of the most, it's from Stanford, it's one of the most popular consensus protocols in use today. So we are going to cover some ground today. The impact of deterministic consensus, and later I'm going to explain what deterministic means in this context. But the impact of classical, let's call it classical consensus, is not to be underestimated. So it plays an important role in Google, Apache, Raft, Microsoft. So there are so many different technologies based on that concept, such as strongly consistent replication, distributed locks on file, leader election protocols, mutual exclusion protocols, commitment protocols in distributed databases, and quite a few others. Time management and synchronization between computers. So how do we define the simplest version of consensus? Let's start there. There is a number of nodes that want to reach a consensus, and some of those nodes are good and some of those nodes are bad. And what bad means could also be interpreted in different ways. Could be malicious, could be just faulty, and could just crash, for example. So there are different models here, different failure models. So every good node starts with a proposal. Say we have Alice, Bob, and Carol. Alice and Bob are good, Carol is malicious. So Alice says, let's agree on 0. Bob says, let's agree on 1. And Carol, I'll prevent you from agreeing. So how do we define the problem in this case? The goal is for every good node to finally decide on a value and terminate. So we have agreement. If any good node decides, they decide on the same, they cannot decide on different values. Termination means that every good node eventually reaches a decision, and non-triviality means that a good node can only decide on a value that was proposed. Why do we need the non-triviality? Because otherwise the good nodes could just agree beforehand. Let's always agree on 0, no matter what the proposal is, right? That's not good. Okay. It sounds like a very simple problem. Believe me, it is not. And okay, so there are different models in which this problem was considered. Different, what is a model? Model means assumptions on how fast, how synchronous the network is, how synchronized the pace of the processors are, what the fault model is, and so on. So here you could see some dimensions of the assumptions in the model. So the model could be synchronous, partially synchronous, and asynchronous. What is synchronous? Synchronous, it means that the network delays are bounded. Then the network processor speed, the processor speed is bounded. So everything is bounded, and therefore we could put a hard time limits on every step. Then it's easier to agree. Why is it easier to agree in a synchronous model? Because if I don't hear from someone for a certain limit of time, I would know that that's other node from which I don't hear is faulty. In asynchronous model, I cannot do that. Maybe that node just slow, maybe the network is slow. So it becomes much harder in asynchronous. On partially synchronous, so asynchronous means no limit whatsoever, and partially synchronous means some intermediate limits. And there are quite a few different models here. Okay, different dimension is the dimension of faults. The simplest failure model is when nodes just crash and stop doing whatever they're doing. So they never recover. A more difficult, more elaborate model is a model in which node can not only crash but later also recover. A different model is a model in which nodes behave rationally. And what do I mean rationally? They try to follow the protocol, but they also try to gain some personal gains within the, in addition to following the protocol. And the worst case is when the nodes behave maliciously, so they try to break the system in all ways possible. Yet another dimension is that of the membership, that is the constellation of all the nodes in the system. Can we assume that every node knows every other node in the system at any point in time? Well, initially that assumption was not unreasonable because we had systems with 4 servers, 4 nodes, right? And we could assume that we configure them all to know each other at any point in time. But of course, like in a data center with tens of thousands of nodes, that assumption becomes a bit unrealistic, both because of the dynamicity and because of the scale. Right, so what can we assume about the membership? Is it known, is it unknown? Is it static, is it dynamic? And there are different combinations, and for each combination the answer and the best solution for consensus would be different. There are quite a few additional questions and assumptions. Can we use digital signatures? What do we assume about the digital signatures? What do we assume about the underlying network? Yeah, we said synchronous, asynchronous, but there's more to it. The behavior of the network in local or municipal network is quite different from wide area networks, right? And yet quite different from wireless networks. So again, choices and choices and choices lead to the multiplicity of problems hidden beyond a single short definition. So let's talk a bit about the impossibility results. We already talked about impossibility of reaching a consensus when 1/3 of the nodes is malicious, which can be alleviated by using digital signatures, but not all the digital signatures can be trusted. There is a second result, which is just as fundamental. If the system is asynchronous and nodes can fail, even the simplest way, fail stop, then we cannot reach consensus. So that's pretty depressing, isn't it? So why is it the case? It's the case because different nodes can. So it's very difficult to distinguish between a faulty node that crashed and a slow node, which hasn't crashed, but from the outside it appears like it might have crashed. And later, like half an hour later, it recovers and said, here I am. But well, we already assume you are not with us any longer. So this is such a fundamental principle, such a fundamental result in distributed computing that I could talk about the impact. So the FLP is named by the names of the author. So the professor who was behind that result was a candidate for Turing Award due to this result. Another example I can give is like an anecdote about the importance of this result. So it was the first Gulf War, 1991, and the Allied fleet of airplanes were flying to Iraq, right? And on the way they entered the airspace of France. Now the traffic control system of France was not designed for that kind of scale, so it crashed. And for half an hour, all air traffic control in France was done manually without any assistance from computers. So later, okay, the interesting part was that there was not a single air traffic incident or accident during that half an hour. So later they had an interview with the chief engineer of the system, and they asked him, how come you were so fortunate? Well, he said, no problem. The system was designed to operate manually if need be. Then the question came, so you designed the computer system to be able to operate it manually? What's the point? Well, he said, for the most of the time it will be done by computers, but we can never 100% rely on such systems. We'll always need to be prepared for the eventuality that the system would not work. And he cited that result. So that's the importance of yet another story about sort of emphasizing the importance of the result. Okay, so how do we get around? So consensus is, okay, why are we looking at consensus and not say at mutual exclusion, and not say at leader election, and not say at distributed locking? Why consensus of all different coordination problems? Because consensus has been proven to be the simplest of the coordination problems. So if we cannot do it for consensus, we cannot do it for any other practical problem either. That's why the impossibility results for consensus are so important. Okay, so far I've been telling you just the bad news, but okay, people still do coordination somehow, right? So how do they do it? What are the techniques? What are the approaches? There are three fundamental approaches. Failures, okay, the first approach is what's called to mask faults. What does it mean to mask faults? If some fault occurs, then the system simply blocks it, doesn't make any progress until the fault is repaired, right? So this is what happens in some critical system in terms of consistency. For example, imagine that the communication between the ATM and the central bank machine, the central bank server, so they get disconnected, no communication. What happens? ATM stops working. You cannot do anything. You cannot, well, sometimes you can provisionally withdraw, but you cannot check your balance, you cannot do anything, right? No communication. And it's blocked until the communication is repaired. Now, if the communication is never repaired, it would never be working again. But this is what's called masking fault. So the system just becomes so slow and irresponsive until the fault is repaired. Okay, the second approach is called the quick trigger approach. So if I suspect that someone is faulty, I say you're out. So slight suspicion, I don't look for further evidence, right? I just say you are not part of the system, we are not doing consensus, you are faulty, I'm not doing consensus with you. So, okay, unfortunately in that scenario, the node, which is suspected as faulty, may not perceive itself as faulty. So it may continue operation. It may proceed with doing some transactions, right? And then the system state would be inconsistent. And then it may need to be manually repaired at the end. So this is the approach taken by for example, by Amazon.com. So in Amazon.com, there have been known cases when the person was not charged for the order. Why? Because there was because of the consensus problem. So Amazon.com prioritizes throughput of transactions, and if sometimes there is a problem with the agreement, the Amazon.com prefers to suffer the financial losses for that particular case. However, it would be worse for Amazon to stop transactions, because Amazon.com gains on the throughput on transactions much more than it would lose on one individual transaction. So that's a different second approach. There is also a third approach. The impossibility result assumes that everything is deterministic, that nodes cannot flip coins. Well, in reality they can. Why not? There have been randomized protocol and solutions, so why not apply those? So by using a randomization, we can overcome this result. And by the way, this is what Bitcoin is doing. However, the problem with the using randomization is that the protocols become much more difficult to analyze. And the second problem is that randomized protocols, they may take a lot of time to reach the consensus, even if they do. So those are the three principal approaches. Now, I would like to show you some consensus solutions, so classical consensus solutions, not the Bitcoin ones. Such classical consensus solutions are used, for example, in Hyperledger, in different projects related to Hyperledger. So they also play important role in blockchain, if not in Bitcoin. But I was thinking how to present, because before you get to understand the advanced solution using Hyperledger, you need to have some basics about consensus protocols. So I was thinking to start by the simpler protocol, which is Paxos. So Paxos, what is it? It's the most commonly used consensus algorithm. Well, today it competes with Raft. It's a fundamental building block for data centers. So it underlies problems and solutions such as distributed leader election lock, distributed resource control, such as the naming service at Google, management of distributed logs, and it's used by most data centers and cloud providers, including Google Chubby, Amazon Web Services, Oracle, NoSQLDB, VMware, Microsoft, IBM, you name it. Let's take a look at how Google uses Chubby. So that's like that's a very simplified illustration of the infrastructure at Google. So we are all familiar with Google Drive, Google Calendar, Google Analytics, and Gmail, right? So those are the top services of Google which are available to the end user. However, internally, in order to build those services, Google relies on additional components, reusable components, right? Additional reusable services which are not exposed to the end user, but which are intensively used by those well-known services. So those include Bigtable, which is like the database at Google, and the Google File System, which is the file system at Google. Okay, those in turn rely on some other components, including Chubby. So Chubby, each time you use Gmail or Google Drive, you would be unknowingly relying on Chubby, which is the implementation of Paxos. Okay, so this was the explanation why it's a good idea maybe to learn a bit about Paxos. So let's do that. So what is Paxos? Let's start from the roles of different nodes in Paxos. In Paxos, there is a client which issues a request to the Paxos system. So what is a request? A request could be, I want to get a log on that particular file. That's a request. Okay, so these are clients. They are not implementing the Paxos system, but they're sending a request to the Paxos system. A proposer accepts the client request, and its role is to publicize the request and advocate the state change to other proposers and other processes implementing Paxos. So in different implementation, maybe a single proposal, maybe multiple proposals. The next role is that of an acceptor. Acceptor executes the agreement and records the state change once agreement has been achieved. Learner, once a client request has been agreed upon by all the acceptors, the learner would take action and, for example, grant a lock on a file. Sometimes a learner called a witness. And leader, so among several proposers, Paxos selects or elects a distinguished proposer called Paxos leader in order to make progress. So those are the roles. Of course, the same node may play multiple roles, but we are not, like, for the sake of clean separation, Paxos introduces those different roles. And for each role, a node would execute a specific protocol. Let's visualize it. What's the typical flow in Paxos? Here's a client running an application. It would send a request to the proposal, I want to get a lock on the file. The proposer would run some internal protocol with vis-a-vis acceptors. And once acceptors reach a decision, they inform the learners, called witnesses or workers, which execute the decision. So once there is a decision reached, that now the lock will be given to that client on that file, now the workers or the learners would perform the actual operation. So Paxos implementation involves all the roles apart from the client. Now, how do we design such a protocol? I find it to be a useful exercise to try to think how you would run such a protocol and see the problems and then try to incrementally fix the problem and make the protocol more and more complex until you end up with the final version of the protocol. So let's do that. So first, there are different versions of Paxos. So the simplest version is called one-time Paxos. One-time Paxos called or basic Paxos. It's one decision only. One decision only means, okay, let's grant the lock to that particular client, and that's it. And then the system stops. Of course, it's not a very practical version of Paxos. Today we'll see the realistic version of Paxos. But this is the simplest version. And even that version is not easy to solve, right? So this is where we start. Okay, so in the basic Paxos, there are the following messages, types of messages. Prepare. In a prepare message, a proposer sends a message with proposed value to the acceptors. Confirm. The acceptors confirm the reception of the proposed value. Accept. The proposer asks the acceptors to accept. Accepted. The acceptors respond, indicating that they have accepted the value. So accepted message sent both to the proposer and to each learner. So learners act as a secondary storage mechanism. Let's visualize that. So prepare with the value, confirm, accept, accepted. It's called like two-phase protocol. So one round or two round protocol, one round of communication, second round of communication. There is a basic proof, by the way, that we need two rounds. We can never reach consensus with one round only, at least in an asynchronous system. So what's the problem? The problem, of course, is there could be another acceptor doing the same. So now, and it could be it could well be the case that different pair messages would reach different acceptors in different order. So acceptors would confirm one value, some other acceptors confirm the other value. So that's not good. We need to avoid it. So the classical technique introduced in such a situation is to break the symmetry with proposer IDs. So what we do here is that pair message would include the ID. So every node, in this case, every proposer is given an ID, which could be like just a number, or could be the IP address, could be anything. It must be unique, and it must also be sorted. So we would know which ID is bigger than which other ID. So a pair message would include the ID of the proposer. Same here. Now, what happens here is that both values P and Q, both proposals would be confirmed by different processes. However, what happens here is that then the proposer would send the accept message, and the accept message would include both the ID and the proposed value. And then what the acceptors do, they compare the ID, and they break the symmetry, for example, by selecting the biggest ID. So even if this acceptor send confirm to P, it would see that Q is bigger than P, and then it would accept the value from Q, overriding the previous confirm. Okay, the next problem is, of course, failures of, okay, in this case, we consider failures of proposers. So let's assume that at this point in time, Q failed. Okay. Then the protocol is blocked again. We need to do more. We need to overcome failures. How do we do that? So let's make the protocol a bit more complex, step by step. So we need to monitor proposers for failures and establish additional proposers if the current one fails. That's one thing we need to do. We also need to index proposals by an increasing sequence number and give them timestamp. So the timestamp would include two things: the ID of the proposer and the increasing count from that proposer. And timestamp is used like the ID, not of the proposer, not of the node, but the ID of the proposal. So the same timestamp would be used in the prepare and accept message to indicate that it refers to the same proposal. Now, we don't call confirm it any longer, it's a promise. Acceptors promise something to the proposer. What do they promise? They promise that if the timestamp in the prepare message is smaller than or equal to any timestamp previously received by the acceptor from any proposer, the acceptor would ignore the proposal. Otherwise means the timestamp in the prepare would be bigger than any timestamp previously received. It returns a promise to ignore all future proposals with a smaller timestamp. So this way, acceptors may give a promise to multiple proposals, but only if those proposals have increasing timestamp. So let's see how it works. The same scenario, P and Q push in different values, and here, so Q has a bigger ID, here Q fails, crashes. Okay, so P sends a paper, this time with the timestamp 1P, 1 because it's the first proposal from P. It's a count. And then it would get a response promise 1P. And the Q will get a responses promise from the two other acceptors promise 1Q. Actually, also from this acceptor, right? Because this acceptor will see both promise 1P and promise 1Q, but 1Q is bigger than 1P. So it will, even though it sent a promise 1P, but promise only means to ignore proposals with smaller timestamp. But 1Q is a bigger timestamp, so the same acceptor would send the same, another promise, right? Okay, so then there is a crash. Then there is a timeout. We monitor processes for crashes. And then at this point, P realizes that there is no solution. So what does P do? P increases the counter from 1 to 2 and sends another attempt, another proposal, 2P. Okay. Okay, so that was just the pay pair part, right? So then after P, okay, sorry, it's a different scenario. I should come back here. So what would happen here is incomplete, right? So here P sends a proposal to P, and which would be, then it would get promises from all three acceptors, and then it would send accept to P, and will get accepted to P from all three acceptors. So that would be a good flow without further failures. Now let's take a look at the different scenario. In this scenario, in this scenario, P was winning with 1P, so it sent accept V1P. Then the three acceptors accepted the proposal. However, P crashed in the middle. So in this particular case, in this particular scenario, okay, then Q, after all this happened, Q sent pair 1Q, got 1Q sent accept Q. Then what do we do? If the acceptors go along with the second proposal, the two proposals are accepted. If they ignore the second proposal, then the system is blocked because this one has failed. So we need more changes to the protocol. And the next change is that promise messages includes most recent previously accepted value, if there was a previously accepted value. If there was no previously accepted value, it would just indicate, the promise message would just indicate there was no previously accepted value. And this addition allows proposers to keep track of the previous attempts. So how do the proposers take this into account? So the proposer would send a proposed message, would get a promise. If, according to the promise, there were no previous attempts, the proposer would just include its own request it was advocating. However, if there was a previous attempt, then the proposer has to switch its own wish to the value used in the previous attempt. And acceptors perform the same timestamp check when accepting as when promising, right? So only increasing timestamps. So with that addition, the Paxos protocol may accept, not only promise multiple proposals. However, if it accepts multiple proposals, all accepted proposals will have the same value. So let's see an example. The same scenario, right? Failure here, paper 1Q. The main difference here is that the promise message would include V. This is the main addition. Right? Where does V come from? From the previously accepted value. And this allows Q to learn the previous attempt. So then, instead of sending accept U as it originally wanted, it replaces U with V. Okay, and it will get it accepted, so both proposals are accepted. However, it doesn't matter because they both contain the same value. There is no disagreement. The next problem in Paxos is called dueling proposers. There is first, okay, P sends 1P, promise 1P null because there was no previously accepted value. Q, slightly later, sends prepare 1Q, gets promise 1Q null. P sends accept V1P, it fails because now the acceptors already promised to 1Q. They cannot accept 1P. Then let's suppose that Q became slow. So after a timeout, so P doesn't know if Q failed or just became slow. Again, the FLP is out, the impossibility. It's impossible to distinguish between a slow process and the failed one. Okay, so P would send, after a timeout, would send prepare to P and get, in a response, promise to P null. Wow, because 2P is bigger than 1Q. At this point, Q wakes up, says, here I am, and continues with its proposal, which is 1Q. So accept U, 1Q. Well, it would not be accepted because it was already promised to 2P. Okay, now P is slow and Q becomes fast. So after a timeout, there would be prepare to Q, sent by Q. So in which case it would promise it would get a response to Q now. In theory, this duel between the two proposers could go forever. Of course, it's very unlikely because in order for this to happen, they need to play along so one would become slow exactly when the other becomes fast, right? And vice versa. So in order for this scenario to continue for a long time, there is a need for a very specific schedule, which is unlikely, right? One thing to mention, Paxos does not solve the problem of dueling proposers because of the impossibility result. Because of the impossibility result, so we cannot reach consensus in any situation. So Paxos just assumes that it would not happen for a very long period of time. Yes, please. What is the promise? Is a message sent by an acceptor to a proposer, and the semantic of a message, yes, I've seen your proposal. I promise not to accept any proposer with a smaller timestamp, only with bigger timestamps. That's the promise. Sorry, could you repeat the question and also speak up a bit? Mhm. There is no such a thing as the same time. So one would need to be the first. Yes. Well, okay. It goes by the timestamp, right? So, but if there was no promise from the acceptor not to accept proposals with smaller timestamp, then it would accept any proposal with any timestamp. All right. Next problem. So far, we've only talked about failures of proposers, right? But acceptors can also fail. So what do we do about it? Well, according to what we said, the protocols we were talking previously, it would block. Why? Because proposer wants to get both promise and accept from each and every of acceptors. Okay, so we need to further modify the protocol and make it even more a bit complicated. Okay, so the idea, we collect the responses from say, a majority of acceptors instead of all acceptors. If we only collect the responses, or if the proposer is satisfied with getting the responses from only a majority and not all acceptors, then the system can tolerate failure of minority of acceptors. So the proposer can send to all, there are different variations. The proposer can still send to all acceptors, but only wait for a response from majority, or it can only send to a majority. So this further complicates the protocol, as we'll see, because it results in the possibility of two different values being accepted by different acceptors, as we'll see. However, only one will be accepted by majority, the other one would only be accepted by minority. And then the learners now need to be careful. They can act not when they see one accept message. They can only act when they see accept message from a majority. So in this scenario, we have accept V1P, accepted, and then we have two failures at the same time. One of P and one of say, this proposer. So the message never reaches the accept message, never reaches this acceptor, and this acceptor either, only this acceptor. Okay? So this acceptor responded with accepted. These two acceptors, they have never heard the accept message. In the meantime, what happens is that Q sends prepare 1Q. Now, previously, all acceptors have seen prepare 1P, but 1Q is bigger, so it's okay. So these two acceptors would send back promise 1Q null because they have seen this message. So they can still promise. And null because it was not, according to these acceptors, there was no previously accepted value. Now Q sends accept U 1Q, and it also fails to make it more interesting. And then these two acceptors have absolutely no problem. They send back accepted U1Q. So now we have a situation where both values were accepted. Here, this acceptor accepted V, these two acceptors accepted U. However, only U was accepted by majority. V was only accepted by minority. Please note that this scenario is only possible when the sets of acceptors is not overlapping, right? Because if there was one acceptor in the intersection between what P was doing and what Q was doing, then the acceptor in the intersection would be able to detect and send back the feedback, so it would not accept both proposals. These two acceptors can send back accepted U1Q because they have not seen the message from P. Oh yeah. Well, Q sends to all, but let's suppose that because of this failure, it would not reach this acceptor, right? So it turns out like it's like P and Q. As one, it gets promise from V, and from these two, it gets promise U. Now, it needs to know that it would need to further push U and not V. So how would it know? It's a bit tricky, right? So the challenge here is for P to realize that you got the majority and not V. How would it know that? So the trick is to use the previously accepted value with the highest timestamp. So the promise message now responds back not only with the value of the previously accepted proposal, but also with the timestamp of the previously accepted proposal. So V was accepted with the timestamp of 1P, while U was accepted with the timestamp of 1Q. And now at this point, P compared the two values which we received back promise messages. It would realize that 1Q is bigger than 1P, and because of that, it would select U and not V. So that's one of the trickiest parts in the Paxos protocol. So now we are ready to see the final version of the protocol with all the complications that we've seen along the way. So the protocol proceeds over several rounds. The success has two phases. The first phase is prepare, and the second phase is accept. In the prepare phase, there is prepare and promise. In prepare, the proposer selects a quorum of acceptors. It sends a prepare message to the selected quorum, and the message contains a timestamp, which is where the counter must be greater than any previous sequence number used by this proposer. And in response, it would get a promise, which is again, if the timestamp is smaller than or equal to any timestamp previously received by the acceptor from any proposal, the acceptor ignores the proposal. Otherwise, it returns a promise to ignore all future proposals with a smaller timestamp. And if the acceptor accepted the proposal in the past, the promise message must include a corresponding sequence number and accepted value. Then comes phase 2, the accept phase, in which the proposer waits for the promise message from all quorum nodes, and then it selects a value to be accepted. And if none of the promise messages contains a previously accepted value, then the proposer may choose any. Otherwise, it would find the promise message with the highest timestamp and chooses the value in that message. So, and then it selects a quorum of acceptors, usually the same quorum to which it sent the prepare message, returns the request with the chosen value and same timestamp as in the prepare message. And finally, there would be an accepted message, and acceptor accepts an accept request with timestamp t if and only if it has not promised to any preparer with a bigger timestamp. And then the accepted message is sent both to the proposer and to every learner, otherwise ignore the request. And when a learner gets accepted with the same value, it could get accepted with different values. When it gets accepted with the same value from a quorum, at this point it may act. So that's the complete protocol. And this is just for the simplest version of Paxos. Okay, let's continue. A more practical version of Paxos would be what's called consensus on a shared lock or ledger, which is useful in blockchain and which is useful also in other contexts. Because in reality, what happens in reality is, let's consider the service which grants locks on files. It would not just grant lock once. It would be a sequence of decisions. Okay, at this time, first let's grant lock to this on this file to that node. Then let's grant lock of another file to another node, right? Then let's take the lock back, right? So it's all in practice. It's always a sequence of decisions. So it must be a linear sequence, but it's a sequence, not just the one decision, right? So this is why we can see it as a lock. The first operation would be transaction. Okay. So then what would be the second operation, right? So there must be agreement about second operation. There must be agreement about third operation. And again, curl is trying to prevent all different agreements. So this is similar to the problem which is solved in Hyperledger Fabric, for example. This is just one system, blockchain system, which does it, but there are many others. And again, Google Chubby effectively solves this variation, this flavor of the problem, with a sequence of decisions. So what do we want in terms of the requirements for the solution? In the solution, every node decides what's on each entry, and there is additionally a need to define fairness and disallow gaps. What does it mean, fairness? Fairness means, or what does it mean to disallow gaps? Gaps means that we cannot decide on operation 3 before we decided on operation 2. So that would be a gap, right? So the decision must be taken in a sequence. So historically speaking, what was the role of probabilistic consensus for Bitcoin? As I mentioned, the FLP impossibility result only holds for deterministic guarantees, not when you flip in the coin. If nodes are allowed to flip a coin and change their proposal, consensus can be solved with high probability. So the idea of a probabilistic protocol is that every node is now allowed to send multiple proposals, right? Before deciding, even if there are no failures. Previously, the node would be only sending different proposals in case of failures or problems. Now, with probabilistic, the node can just randomly decide on a different value. So the idea of a basic probabilistic protocol is that, again, like there is a need to decide between two proposed values, right? So the proposal flips a coin when choosing which value to decide from. And the reason is that, like, the splits, it has been shown that the splits, if, for example, a subset wants to go with one value and a subset of nodes wants to go with a different value, such configurations are shown to be unstable. So if the nodes start to flip coin, it's very unlikely to repeat itself all the time. And this is why eventually there would be a majority for one value over the other. So how do we define probabilistic consensus? We need to slightly change the problem, right? So each node still decides once. So the probabilistic termination would mean that every good node decides with probability 1. And probabilistic agreement means that if two good nodes decide, the value is the same with probability 1. So it's all the guarantees are also probabilistic. So it's not easy though to compute the probability over distributions. Well, so what was the importance of this type of algorithms before Bitcoin? It was theoretically interesting, but was virtually never used in practice, right? Because it was it was perceived as more robust and scalable, but the scale was never there in practice. One interesting tidbit: Chubby, even today, like the infrastructure of Google is quite comprehensive. It runs on many tens of thousands, maybe hundreds of thousands of servers. However, all of them are served by a single deployment of Chubby, which runs on 5 servers. With some redundancy baked in, so if one of the servers fails, then there would be some backup server which would immediately be brought up at this point. So, but turns out that 5 servers is enough to serve the rate of request from all of the Google infrastructure. So why 5 servers? Because it's much easier to manage the membership. And that's an interesting part. We're going back to this theme several times throughout this course. In this kind of classical agreement protocols, the number of servers is a much bigger impediment to scalability than transaction rate. So the scale was never there, and therefore there was no need to run the probabilistic consensus. It also offers slower conversions and lower throughput. It's more difficult to analyze and formulate guarantees. It's more complex. And there was not a single commonly used system in the industry before Bitcoin, which was based on probabilistic consensus as opposed to the classic consensus. Now, Bitcoin came out in 2009 and became the first popular use case for probabilistic consensus. So it's probabilistic consensus on a shared log. It's also called Nakamoto consensus, in which a node may decide many times on the same entry, on the same block, so the same block height. It's called the same number with a given number. So the node may change the decision many times. It's allowed. So we need to define the condition of conversions to reasonable transaction finality. So we can no longer view it as a sequence of independent instances, because now the instances are also dependent on each other. The first attempt came out in 2015. It's called the Bitcoin Backbone Protocol, Analysis and Applications. So this was the first attempt to define the exact problem of convergence and consensus solved by Bitcoin. It's quite an interesting paper. So it defined 3 different conditions. I'm not going to cover them. But later, the definition was also extended, so the research on the exact definition still continues. And the problem solved in other cryptocurrencies is slightly different. So we cannot reuse the definition from Bitcoin. One interesting observation is that so far the branching in Bitcoin was not a big problem. So far we have not observed very long branches. We talked about branches in Bitcoin last time. But the longest observed branches were of length 2 each. Not very long. However, this is because of the average time to produce a block, 10 minutes. In Ethereum, for example, same ideas were used, but the time was much shorter, and the branching was much higher compared to Bitcoin. We are going to talk about Ethereum separately. So what you see here is a very fundamental performance trade-off between classical protocols like Paxos and the more modern protocols based on the probabilistic consensus. So you can see 2 dimensions here. One dimension is that of nodes, while the other dimension is that of transactional throughput. And then that standard POW protocols such as Bitcoin, they are very good with respect to the number of nodes. They are quite low with respect to the both throughput and of transactions. So high latency, low throughput. And then we have standard protocols like Paxos, which are much better in terms of their latency and throughput, but usually run on a very small number of nodes. So there have been many attempts to bridge over the gap, right? You see like the bipolar distribution between the 2 extremes. So there have been an attempt to bridge over. All attempts were only had some sort of moderate success. We are going to talk about some of those attempts in this course. But yes, today we are going to cover, for example, Bitcoin NG, which is much better than Bitcoin, but it comes with a price tag. And there have been attempts to parallelize the execution of Paxos protocols. Now, I would like to talk, so far we only talked about Paxos. I picked Paxos because I believe it's the easier protocol to learn, and it's also simpler than other protocols. So Raft is a bit similar to Paxos. I'm not going to cover Raft, even though it's another very important protocol and also used in Hyperledger Fabric. But I would like to talk about the difference between BFT protocols and the Paxos. So BFT protocols operates in two rounds, right? The first round prepare, the second round accept. BFT protocol, so one thing about Paxos is that it only tolerates crashes. It does not tolerate, as presented, it does not tolerate Byzantine behavior. Can we extend Paxos to tolerate Byzantine behavior? The answer is yes. I'm not going to show how because it's much more complicated. We need to introduce a third round. So BFT protocols usually take 3 rounds, not 2 rounds. And of course, the third round contributes to the latency, needless to say. So standard BFT protocols, they can be a bit parallelized, so therefore improving the number of nodes. Also later today we'll talk about sharding, which also helps with BFT protocols. Still, like bridging the gap is an incremental endeavor. And this is the end of this lecture. All right. Let us start the second lecture today. And the second lecture is dedicated to blockchain scalability. So what we'll see in this lecture is basically we already know that blockchain has some scalability barriers. So what kind of techniques system designers are using to break those barriers? And I should also give the credit, this lecture was mostly prepared by a postdoc working with me. His name is Tiago Garrett. All right, so the limitations of blockchain scalability are well known. And so here you can see some collection of the news complaining about the pace of transactions in Bitcoin. Why hasn't my transaction confirmed yet? So what can we do about it? I'll be talking about 5 different techniques. So the first technique is there are some configuration that affect the scalability. The most prominent one, the most famous one is the block size. So the second technique is try to use more scalable protocols. How do we do more scalable protocols? In Bitcoin NG, which we'll see in the third lecture today, they're using microblocks instead of blocks. In Algorand and quite a few other cryptocurrencies, they're using committees. So instead of consensus being run by all the nodes, nodes select the committee representatives, and the consensus is only run by the representatives. The third technique is to use parallel structures instead of chains. So we'll have 2 lectures in this course on DAG-based systems. So where the blockchain is building not a chain of blocks, but a more complicated structure with parallel blocks and parallel transactions. So that allows some degree of parallelism without the need to basically to build all a chain, sequential chain out of all proposals. So that's another technique to improve the scalability. The fourth technique is building on top of a chain instead of changing the core of the protocol. So that's the idea of Lightning networks and off-chain transactions in Bitcoin, and that's the idea of what's called layer 2 in Ethereum. So this is what this lecture would be mostly about. And the fifth direction is that of sharding. So those are like the 5 main techniques used to overcome scalability barriers in blockchain. So I'm not going to talk much about number 2 and number 3 because we'll have dedicated lectures on that. But I'm going to cover 1, 4, and 5. So let's start from the block size. What's the deal with the block size? Why is the block size such debated topic in Bitcoin and in other cryptocurrencies? Because there is a clear trade-off. What happens if we make very long blocks? Well, there is a positive side, there is a negative side. The positive side is that we would be able to include more transactions in a single block. Therefore, in the best case, we should be able to increase the transaction rate, the transaction throughput. What's the downside? The downside is that longer blocks take longer to propagate. Like they are more prone to failure, so the rate of failures would increase a bit. And longer propagation leads to higher risks of attacks. It may also lead to higher, and because of the longer propagation, we may also end up with a higher branching. So there is a trade-off. And there are always proponents and detractors, right? So in this context, I would like to mention SIGWIT and SIGWIT 2X. SIGWIT came out around 2013, if I'm not mistaken. It was a soft fork of Bitcoin with two components. After the block structure, two components, two ideas. The first idea was to alter the block structure so as to move the location of the signatures such that the signatures would not take time during the verification, or at least some of the operations would be performed faster. So it was an optimization about the block structure. But the more interesting was the second change, which was to allow block size to be more flexible based on block weights. So according to SIGWIT, each block may be assigned a different weight, and the higher the block weight, the longer the block is allowed, the maximum size of the block is allowed to be. So how do we decide on weights? Well, there are different components that affect the block weight. But ultimately, the most important part is that this resulted in longer blocks in practice and higher transaction throughput. And it was a soft fork, so again, like it was backward compatible. The newer system after the change was still being able to work with the old clients from before the change. So it's a soft fork. Therefore, it was accepted, and most Bitcoin clients today adopt SIGWIT. Now, in comparison, there was SIGWIT 2X, which was a hard fork, and it was more straightforward. Let's double the size of a block. So it was pushed by the miners, but it was mostly opposed by node operators and system designers. And it was highly controversial, so there was like debate for about a year, and at the end, it was abandoned. So this is one exemplification of what people do regarding the configuration of blockchain. Now, the next technique, so that's obviously the simplest technique of them all. The next technique we are going to consider is building on top of a chain. So the idea is to create something outside the main chain. How do we do that? So two on-chain transactions, there would be one transaction put on the chain whose purpose would be to start a separate chain, let's call it a side chain, and there is a second transaction which would end the separate chain and transfer the results back to the main chain. So everything that occurs within the side chain is invisible to the general blockchain participants. Only the end result is recording due to the second transaction of the two. So why is it faster? Well, it's faster because we don't need to run consensus on the transactions. Imagine that a side chain would include 100 transactions. We don't need to include those transactions individually and run consensus on them. There might be small number of participants in a given side chain, maybe just 2 participants or 3 participants instead of all the large scale. Because it's created coordinatedly. Say 2 nodes decide, okay, now we are going to do a lot of trading between us, so let's do it separately from the main chain. In this case, they create a side chain. So it would be much faster for them, because now they don't need to push all those transactions. They don't need to pay the fees to the miner for each individual transaction. All they need is one big transaction at the end in order to flush it back to the main chain. So we'll talk about Lightning Network in Bitcoin, and we'll talk about tier 2, layer 2 in Ethereum. Lightning Network in Ethereum based on micropayment channels established between just two parties. And so the micropayment channel is created with a special transaction called a funding transaction, which locks fund on the main chain. So it takes fund from the main chain, UTXOs. It locks them, so now they are not usable on the main chain. And now, there is a period during which transactions are done on the side chain, and at the end, those the funds from the side chain would be flushed back to the main chain, at which point the UTXOs may be unlocked or may be spent. And in case of misbehavior, so what happens if the two parties disagree while doing transactions on the off-chain, on the side chain? Well, it's more difficult, of course, compared to, so on Bitcoin we have no dispute. Everything is visible, right? On side chain we can have disputes. So disputes would take long time to resolve. Probably long. So in that case, the parties would probably lose in terms of the speed. I'm not talking about financially. I'm saying in terms of the speed of completing all transactions, the parties would lose if there is a dispute. But hopefully, most of the side chains would be resolved without disputes. So here's an illustration, right? So Bitcoin blockchain, Lightning Network, right? So there are two nodes, A and B. Say node A has balance of 5 Bitcoin. And then the node would send 2 Bitcoins to the Lightning Network. That's the starting transaction. And then we have, it's a type here. It should be node B with a different balance of 2 Bitcoins, which would send 1 Bitcoin to the Lightning Network. So now on the Lightning Network, this one starts with 2 Bitcoin, and this one starts with 1 Bitcoin. So then they do some transactions between them. Say, for example, node B would be receiving 0.5 Bitcoins from node A, and then later node B would send 1.5 Bitcoins to node A. And node B can also send some transactions outside of the channel. So in this case, there is transaction 3, which transfers funds, in which funds are transferred to node X. And then at the end, there would be the end transaction, in which the results for node A and the results for node B would be sent back to the main chain. So again, the advantages and the disadvantages. The advantage is the throughput and the latency are limited only by how fast the two parties can interact with each other. There are no fees to the miner. And there is another advantage. This scheme can also work cross-blockchain. So some of the bridges, last time I mentioned interoperability between different blockchains. So some of the bridges work based on such channels. Disadvantages. So we need to constantly see the main chain if the other party is trying to publish some premature settlement. So the two parties on the side chain do not trust each other. Okay, so they need to also watch what the other party is. So each party would need to watch what the other party is doing with respect to the main channel. Main chain, not channel. And the disputes can be resolved slowly. And opening a channel is subject to the latency of the main chain. So you do not want to create a side chain in order to do just a couple of transactions. You only want to do it if you want to perform a long sequence, a bulk of transactions. Ethereum, layer 2. So in Ethereum, layer 1 is the technology, is the blockchain technology itself, while layer 2 is what you build on top, right? In essence, it's the same principle as Lightning networks. So in layer 2 in Ethereum, we batch multiple transactions into a single one, sent to the main channel, main chain, sorry. And there are multiple layer 2 solutions. Those solutions differ by the trust model between the participants. They have different goals, and therefore they're suited for different applications. They use different consensus protocols, and so on. So let's take a brief, I'm not going to present everything, and by the way, layer 2 was introduced just a couple of years ago, so or 3 years ago, so it's still in development. So I'm only giving you some taste, some overview of what of the things that exist in layer 2 scaling on Ethereum. So first, Ethereum has state channels, which are pretty much the same technology as Lightning networks in Bitcoin. However, it also has optimistic rollups, ZK rollups, zero-knowledge rollups, Validium chains, plasma chains, and side chains. So they all serve the same purpose, but they have slightly different solutions and models. So what is optimistic rollups? The idea behind optimistic rollups is to perform computation off-chain, publish results on the main chain, and then bundle hundreds of transactions in a single transaction. So far, it's the same as side channel. The main difference is that no proof is provided. The main difference, when you publish the final results of the side chain on the main channel, on the main chain, so the question is, what exactly do you publish at this point? How much of the history of what happened on the side chain do you publish? How stringent the proof from the side chain need to be? How much privacy do you want to preserve with respect to what happened on the side chain? So these are some of the differences between the solutions. So in optimistic rollups, there are no proofs. In that sense, they are optimistic. They hope that lack of proofs would not cause any problems. So optimistic rollups, the main idea is that it saves computation costs, right? Because the computation, the main point in optimistic rollups is that all the computation, transaction in Ethereum is not transaction in Bitcoin, in the sense that they can be like a programs. They can perform some, maybe not very heavy, but at least non-trivial computation. So there is significant cost of performing computation on the main chain, main net of Ethereum. And the main motivation for optimistic rollups is to move the computation. So it's not the fees, it's not the same as, the motivation is different from motivation in Bitcoin. We want to move the computation to offload the main net of Ethereum. So optimistic rollups save computation costs, but doesn't improve the latency a lot. Next, we have zero-knowledge rollups, in which we bundle hundreds of transactions into a single proof, and we provide a zero-knowledge proof without disclosing the details of transactions. So we provide proofs without disclosing the details, zero knowledge. Side chains is a reserved term can be confusing because sidechain is just a concept, right? But in Ethereum, sidechain is a reserved term. It's for specific types of layer 2. What type? So sidechain in Ethereum is essentially a different ledger with its own consensus algorithm, everything, its own storage, everything. So, in the middle of running on mainnet, you decide to start your own ledger, right? And you do everything on a different ledger, proprietary ledger, probably smaller number of participants, maybe more scalable consensus. And then at the end, you decide to flush the result back to mainnet. And plasma chain is something in between. So it uses the idea of optimistic rollup, so perform computation off-chain. It also has its own chain, but it's not a full-fledged ledger, unlike side chains. So here's an illustration. It's called Matisse, a Matic sidechain. Yeah, sorry for the quality of the picture. It's not really visible. So anyway, this is the mainnet of Ethereum, and the mainnet can be divided into different points, into different checkpoints. So there is a checkpointing between the main chain of Ethereum and the side chain. That's the idea, the checkpointing. They synchronize about the result periodically, or there are certain triggers for synchronization between the main chain and the side chain. Okay, so this is what I wanted to say about layer 2. Now the next technique is sharding. What is sharding? Sharding is layer 1 solution. So we are changing the fundamental technology of blockchain. We are not building on top of it. What's the idea? Nodes are split so in separate shards. Shard is a fancy name for partition. So nodes are split into different partitions, and each shard maintains a separate blockchain. And the transaction, so everything is split between the shards. The nodes, the storage, and the transactions. So, for example, how do we split? For example, we decide that Dr. Moody would be on shard 1, while I'll be on shard 2. So all my data would be on shard 2, while all Dr. Moody's data would be on shard 1. So, and then if most of the transactions would be within the same shard, so we need to be smart about how we divide, right? We want most of the transactions to be within the same shard, but some of the transactions can be cross-shard, and we need to have provision for that. So here's an illustration, 2 shards, and we can even have branches within each shard, right? Because it's like a separate blockchain. And then we can have a cross-shard transaction. Cross-shard transaction would be like me transferring some funds to Dr. Moody. This transaction would need to result in subtracting my balance and adding to the balance of Dr. Moody, right? So it affects the state of both shards. Cross-shard transactions are much more expensive to implement in a sharding system compared to intra-shard transactions within the same shard. Okay, so why is it a good idea to use sharding? Sharding is a popular technique, not just in blockchains, but in general, in a replicated system. So it helps with scalability. First and foremost, we split the nodes. So the consensus needs to be run only on a per shard basis, only between the nodes of that shard. And the smaller the number of nodes, the faster it is, and the more robust. It also helps, of course, that we split the storage, right? So now there are some nodes which only store my data, and some other nodes which store the data of Dr. Moody. So per node, it's less data to store. So it also saves on the storage cost, well, usually it's the consensus cost. It also helps with the computation, right? Because as mentioned, transactions in Ethereum and in other systems can be reasonably computationally extensive or intensive. Therefore, it's good that not every node needs to execute every transaction. So that's the idea of, the benefits of sharding. However, unfortunately, sharding lowers security. Imagine that you use sharding on Bitcoin, just for the sake of illustration. There is no sharding on Bitcoin, but imagine that there is, because it's the same principle as sharding on many other systems. So in Bitcoin, in order to successfully launch a double spending attack, which we discussed, the attacker needs 51% of the total mining power in the network. In the shards, okay, so this is what you see on the left-hand side. On the right-hand side, on the other hand, imagine that there are 10 shards. In this case, the attacker only needs instead of 0.51, the attacker needs only 0.051 fraction of the total mining power in the network, because it's much cheaper to overcome the mining power of a shard compared to the entire system. Another problem is with Byzantine nodes. We said that, so we know that Byzantine consensus can only be reached if more than 2/3 of the nodes are honest. So if you have too many Byzantine problems, it's a problem. Too many Byzantine nodes, it's a problem. Now, when we divide the nodes across shards, we may be unlucky. We may decide to put all Byzantine nodes in the same shard. And then they would do much more damage there compared to the entire system. So that's another problem with sharding. So let's take a look at one sharding system in the context of blockchain. It's called monoxide. In the system, the shards are just called zone, and there is a number of zones, which is a power of 2. The system includes efficient cross-zone transactions, which they call relay transactions. Nodes are split based on their ID. They used to mine blocks. So in this case, it's like one of the most of the simplest, but also most typical technique to decide on the shard to which the node belongs is just to randomly to use some hashing on the ID of the node, right? And produce some number, and essentially it's like random assignment. The one interesting idea of monoxide is they use the Chukunu mining. Chukunu is the word for arabesque in Chinese. So the idea of mining power of or crossbow, mining power of each zone is similar to the whole network. Okay, we are going to talk about Chukunu mining in a bit. And there is also concern about how to do communication between the shards effectively. So they use distributed hash tables for further discovery, and they use some swarm protocols. Let's take a look at the relay transactions in monoxide. Imagine that there is a transaction which transfers some funds from the user in zone A to the user in zone B. Okay? So what monoxide does, it splits such a cross-shard transaction into two transactions. One transaction would be to withdraw funds from the user in zone A, and the second transaction would be to deposit funds in the user account in zone B. Now the point monoxide is making is that the deposit can be delayed. So the withdrawal needs to be immediate to make sure there is funds, but the deposit can be delayed a bit. So this is illustrated here, right? So the transaction relaying, right? So the deposit, the withdrawal is added to this block in zone A, this shard, while the deposit will happen in a later block in zone B. The latency is relative to the initial transaction, right? So obviously we don't want to delay it too much. Now there is an interesting complication that arises from branching, because each shard may have its own branching. So you see what happens here? What happens here is that initially there was a block A in zone A, and that block included a cross-shard transaction that transferred funds to zone B. So you see there is a relay transaction here. But later, a different branch overcomes this. However, while it happens, or before it happened, before block A became abandoned, what happens in zone B is that the relay transaction successfully went in, was confirmed, then later we had more blocks on top of it, and now we cannot easily cancel the deposit transaction. We cancel the withdrawal. We cannot easily cancel the deposit. So we need to compensate for that. And there's a special mechanism in monoxide to compensate for such a situation, which is a bit complicated, so I'm not giving the details. Instead, the point is to explain the typical problematics of using sharding in such systems. Chukuno mining. So in Chukuno mining, a miner can use a single POW solution to create multiple blocks at different zones simultaneously. So that's an interesting concept, right? Because, okay, first of all, the idea to allow the same miner to create multiple blocks in different zones, right? Because in monoxide, the partition between the nodes it doesn't need to be perfect, and the same miner can participate in more than a single zone, can participate in multiple zones, and can contribute blocks in multiple zones, but maybe not all zones, a subset of zones. Multiple, plural, but not all. And in this case, a single crypto puzzle allows the miner to produce multiple blocks, but not more than one block per zone. And the difficulty is the same in each zone. So we need to adjust the difficulty like in Bitcoin, but we have to make sure that the difficulty stays the same across different zones. And there are also security guarantees which rely on all miners employing this strategy. So there is quite an interesting proof of security guarantees due to using Chukuno mining. So again, this is just a very high-level illustration of the typical techniques used in sharded blockchain systems. And this is the end of the second lecture today. Hello, hello, hello. 1, 2, 3, 4, 5. Okay. Um, so our third lecture today is about two specific blockchain systems called Bitcoin NG and Algorand. So we study those systems because they had a profound effect on the design of later blockchain solutions. So what are Bitcoin NG and Algorand? Bitcoin NG is just an academic paper. It's not really a system. It's an academic paper from a reputable lab, blockchain, where they're doing blockchain-related research, from Cornell. And the paper is called Bitcoin NG, Scalable Blockchain Protocol. So Algorand, on the other hand, is an actual cryptocurrency, but it's also based on an academic paper. This time paper from MIT, and the paper is called Algorand Scaling Byzantine Agreements for Cryptocurrencies. And the popularity of Algorand varied across years. I mean, as it's always the case with volatile cryptocurrencies, it usually ranks among 20 most popular cryptocurrencies by the market cap. Okay, so this lecture would be structured as two separate discussions, one of Bitcoin NG and the other one of Algorand, because the two systems have little in common apart from being blockchain. So Bitcoin NG, what's the motivation for Bitcoin NG and what Bitcoin NG strive to improve? Bitcoin, we know that Bitcoin suffers from low throughput and high transaction latencies, which are governed by the block size and the average block creation time. And the block creation time cannot be lowered because of branching and what's called mining utilization. Mining utilization is the ratio of the power that went into securing the main chain. So at this opportunity, I would like to talk about again about the negative effect of branching and the related metric of mining utilization. So the illustration that we see here is, suppose you have three branches, parallel branches. In this case, the mining utilization is that all blocks here have the same difficulty, so there was no difficulty in adjustment in the middle. In this, the mining utilization about one. So the went into the main branch is equal to 1/3 of the work that went into all the blocks, and that's the mining utilization. Why is mining utilization important? It's important because it's an indicator of how secure the system is. If there is just a single chain with no branching, then in order to launch a double spending, the attacker needs to have 51% of the mining power. If, however, 1/3 of the nodes work on one branch, 1/3 on the second branch, and 1/3 on the third branch, then the attacker only needs to have 51% of 1/3, not of the total mining power. So that's why the branching is detrimental and mining utilization is an important metric. It's for the purpose of security, of understanding the security, how much power went into securing the chain. So what's the idea behind Bitcoin NG? The idea is that why do we need to do POW all the time for each and every block? So in Bitcoin NG, a miner performs POW to be elected as a leader for a period of time until another node solves POW and becomes a new leader. And then a leader can propose a transaction, but the critical difference is that sending transactions, unlike becoming a leader, sending transaction does not require POW. It's a cheap operation in Bitcoin NG. So, of course, that leads to much higher throughput and faster transactions. However, transactions require new mechanisms to get secured. So what are the problems? Why is there a problem of securing transactions if we do not secure each individual transaction with POW? In this example, the first leader sent 4 transactions. And then a new leader came up, solved POW, became a new leader, right? And then the new leader decided to disregard T4 from the previous leader and instead included itself. There is nothing, no mechanism that prohibits the new leader from doing that. And now everyone, all other participants are scratching head and trying to understand it. Was T4 part of the previous block? What is T4 part of the new block? And of course, they could have disagreement about that with all the troubles following. So, okay, so why is that an important problem? Because placing the transaction has fees associated with them, right? So in Bitcoin NG, whoever becomes a leader due to POW also gets a reward. That's the same. But who gets the fees due to transactions? So, like according to the classical approach, the leader gets all the fees. So, if T4 is here, then the leader would get the fee. If T4 is here, then the next leader will get the fee. So the next leader has the incentive to just say, no, T4 is mine. So the idea used in Bitcoin NG to solve it is to split the fee between the current and the next leaders. So they would both be happy. How do they do it? So the problem is that if the next leader gets the entire fee, then the current leader will not be publishing transactions at all. What's the point? And the main challenge of Bitcoin NG is how to split the fees. So they've done some extensive analysis, and they showed that there must be at least about 37% fees to the current leader in order to make it profitable for the current leader to publish transactions, and there must be at least 50 plus something percent to the next leader, so that the next leader would not disregard transactions from the previous leader. And so there is a range. And for example, the 40-60% split, so 40 to the current leader and 60 to the next leader works. And that's a nice result, right? So they're both happy. However, okay, so what's the criticism on Bitcoin and GIAN? So far, this is how the system works. What's the main criticism? The main criticism is security issue with the idea. It's too easy for the leader to send different transactions, to misbehave, to send different transactions, for example, to different system participants and for launch double spending, and so on. So we need some complicated additional mechanism for detecting double spending and punishing a misbehaving leader. So they introduced ideas of like a whistleblower transaction, right? So where someone discovers, oh, the leader is faulty, and adds a whistleblower transaction. Okay, how do we know, whom do we believe, the leader or the whistleblower? There are some complicated mechanisms to this end, but okay, I'm not going to cover. But anyway, this is obviously the main problem with Bitcoin and G is that transactions are not as secure as in Bitcoin. They are faster, throughput increase, lower latency, but less security. Another interesting aspect of Bitcoin and G is that it introduced a plethora of metrics used in assessing the performance. Like assessing the performance of the conversions of ledgers is not a simple task. Like there is no universal agreement about what metric should be used in that regard. So the Bitcoin and G took a stab at it and came up with several metrics. So I'm going to talk about 5 different metrics they considered. And again, I'm talking about those metrics because they also have profound effect on metrics used to evaluate later blockchain systems. So first metric, consensus latency, is the time that it takes for a system to converge on a given block. But what does it mean to converge on a given block? So that they actually, like there are several multiple definitions. This is the tricky one. Mining power utilization is the ratio between the mining power that secures the chain and the total mining power. That's an easier one, and it's a security metric. Fairness is the number of blocks produced by a number proportional to the miner's power. So in Bitcoin it is, but if you start playing around with the model and the protocols, it's not always the case. A very important aspect, the reason why crypto puzzles work in Bitcoin for proof of W is the fairness. If I have double the amount of computational power, then in Bitcoin I'll have double the chances to solve a crypto puzzle. But this is very different from majority of protocols. Imagine that I have a non-majority of problems, majority of tasks. Imagine that I have a classical computation and 2 nodes, and one has double the power, second node has double the power of the first node. So, and I need to do some heavy computation for like maybe NP hard, or maybe just calculate product of huge matrices, whatever, but deterministic computation. What's the chances of the weaker node to complete the computation before the stronger node? 0. That's a problem. That's not fair, because then we'll end up with complete centralization. All smaller nodes would abandon the system, only the big nodes would remain. So that's one of the important properties of crypto puzzles, that they provide this kind of fairness towards the smaller nodes, and therefore incentivize decentralization. So we need to be careful about fairness and be able to evaluate, and the way to evaluate it is to see if the number of blocks proposed by miners with different powers is proportional to their power. Two more metrics. Time to win and time to prune. Both metrics are illustrated on this depiction. Time to win is the difference between the time a node appends a block and the last time a different node does not include that block. So here's time to win, right? Is the time between one node appended this block to its local chain, and the last moment when someone else thought that this block should not be appended to the chain. So what is winning in this case? Winning means confirming that the block is in and by all the nodes, right? So before, as long as there is a node which thinks otherwise, we are not winning in this terminology. So again, it's the time between the first moment the block appended to the chain. And I need to use the words carefully. Okay, what's the cycle, right? First the block is proposed, so the crypto puzzle is solved. The crypto puzzle is solved, the new leader is selected, okay. So at this point someone proposes a block, but that's not a victory yet, because maybe there is already a longer branch, right? So only the victory starts only from the moment when someone appends, thinks that this is the winning block and appends it to its local copy. This is when the count starts. And the count ends when everyone thinks it's the winning copy. It's the winning version. Okay, but please note that this is just for one instance, for one block. So for each winning block meaning block on the main chain, we can calculate time to win. However, time to win would differ between different blocks on the main chain. So do we take the average? Do we take the maximum? So in this paper, they consider the 90% percentile of the times. But I mean, we could consider average and maximum. Those would also be interesting. Okay, now time to prune. Time to prune is the difference between the time a node learns. So, okay, time to prune is essentially the complement of time to win. It's how long it takes to abandon the block in a way. It's the difference between the time a node learns about a block which later becomes abandoned and the time it abandons the block. So in this illustration, this branch, so this version of block 2 was created before this version. So it went into the chain initially, and it was abandoned only when this block was announced. Because up until this moment, there were two competing branches. Only at this moment, this branch became abandoned. So time to prune, time between someone proposed, time to prune this block would be the time counted from the moment when someone proposed the block, not proposed, appended it to the local copy of the chain, and the time when it got abandoned due to the propagation of this block number 4. And again, it's counted on a per block basis. So this is the time to prune this block. And we could ask the same question about each block that has been abandoned. And then we can calculate averages or whatever statistical parameters. So actually they define more metrics, but this just gives you the idea about how we measure the convergence in blockchain systems with branching. Mining power utilization and fairness not related to the convergence, but consensus latency, time to win and time to prune are related to the convergence. So this is what I wanted to say about Bitcoin NG. They have a few more ideas, but we are trying to focus on the central ideas in the system, and that is even more true about Algorand. So Algorand, again, unlike Bitcoin NG, which is a paper, Algorand is a real system. And it has about 30 different components, some of which are pretty standard, like the peer-to-peer network. This peer-to-peer network is slightly different compared to Bitcoin, not in an interesting way, so I'm not going to cover it. Instead, I prefer to focus on the elements on the distinguishing elements. The novel ideas in Algorand which affected many later systems. So what are those? The first and foremost was the idea of selecting committee in permissionless system setting. So the system is permissionless. So in permission, when we know the exact people, it's easier to vote and select a committee. When we don't even know, like, how can I select a committee from people whom I do not interact with, whom I do not see, hear, and know about? That's not simple, and this is probably like the main strength of Algorand. And then the consensus is performed only by that committee. So it's also like related to that is one of the first users of proof of stake to select block proposers. So Ethereum adopted proof of stake in 2022. Algorand did it 5 years earlier. And the ideas of Algorand definitely impacted the design of Ethereum. So in Algorand, every node is assigned a weight, and the weight is determined by how much funds you deposit. So that's like the proof of stake. The more funds you deposit, the bigger weight you get. And then the weight affects several factors. It affects your chances to be selected as a committee member in consensus above all. But not only this. Later, when the committee discusses, nodes with a bigger weight in the committee would also have bigger weight in the decision. And the idea of weight is similar. Okay, let's talk for a moment about denial of service attacks. So denial of service attack is when or in this, okay, let's talk about Sybil attacks, right? So in permissionless settings, the danger is that there is no control over identities. So one entity, one node can say, no, I am 10 different nodes, right? And therefore I should have 10 different votes. How do we prevent that? So in proof of work, it's easy to fake identities, but in proof of work, it's decided by the computational power, and you do not gain anything from splitting your computational power, right? So that's protection against Sybil attacks. In proof of stake, you have a stake, right? So you split your stake, you don't gain anything, right? If you want to replicate yourself 10 times, you need 10 different stakes. Uh, there is a difference, however, in the proof of stake in Algorand and proof of stake in many other systems such as Ethereum. In Ethereum, essentially, or in many systems, if you win, then you become. If you win, then you propose a block. That's it. In Algorand, you only get to become a member of the committee, which uses Paxos or BFT, realistically BFT protocols, in order to propose a block. So the committee is using BFT. There is not like the BFT protocol used by the committee is not so interesting in the sense that like it's not novel, right? It's just yet another BFT protocol. But the choice and the selection of the committee is very interesting. So they use cryptographic sortition. They came up with a new cryptographic primitive to elect the committee. And it uses a more general principle of pseudo-random computation. So let's take a look at committee selection. Committee selection is based on verifiable random functions. And that's another cryptographic primitive which we didn't cover in preliminaries, but which plays a significant role in blockchains. So what a verifiable random function? How does it work? Every node, let's assume every node has a public-private key pair. So verifiable, given a secret key, a verifiable random function returns a hash and a proof. So it's not possible to create a hash and a proof without knowing the secret key. Okay? However, verifiable random function applies it to any given string input. And then anyone not possessing the secret key, but possessing the public key, anyone can, given the input string, the public key, the proof, and the hash, can verify that the hash is indeed correct. So you cannot compute the hash, but you can verify its correctness. So this is verifiable random functions, and again, there are many uses in blockchain. So, okay, so how do we select the committee? Every node does the following. First of all, there is a seed which is shared by all nodes. I'm going to talk a bit about how the seed is selected, but for the time being, let's assume that the seed is shared across all nodes, known to everyone, and it's the same seed. It's reliable. So every node can compute, verify a random function using its own key, and apply it on the seed. Then it would compute the fraction of the hash space based on its own weight and the target number of selected nodes. And this way, the node would identify its own interval within the hash, the range of the hash values. And then it verifies that the hash produced by the verifiable random function falls within the interval. If it falls within the interval, it declares itself as being part of the committee. So it's probabilistic. It's based on the weight, the interval. The bigger the weight, the bigger the interval. The more, the more the selected nodes, of course, the more the selected nodes, the bigger the interval. Okay? But still, it's probabilistic, and yet anyone else can verify the correctness. So if the node claims, yeah, I'm a member of the committee, the other needs to verify that claim. So they verify this claim, by verifying, by using the seed, the public key of the claimant, the proof, and the hash value. Now, why is it so important that only that node can produce the hash? Why is it important that no one else would be able to calculate the hash? Because if someone is able to calculate the hash, they would know who is going to be the leader or the member of the committee. And that node becomes a target for attacks. But so because no one gets that knowledge beforehand, the target of the attacks cannot be established beforehand. So it's quite a smart idea. Now, consensus protocol in Algorand is, as I mentioned, very similar to classic BFT protocols. However, committee members with high weights are given priority. There's actually okay, so how is it done exactly? If suppose I have a weight of 5, then I can actually be selected in the committee 5 times. Okay, now, okay, so what does every proposal include? So what do we need to agree about as part of the consensus in Algorand? So every proposal obviously includes transactions. I mean the standard fare, right? So we need to agree about the transactions to be included and the order to be included. However, additionally, a proposal would include the seed for the next VRF computation. And it's also computed in a probabilistic way. So the next seed is computed by applying VRF to the last seed using the private key. And of course, the proposal needs to include the proof of the computation, as always, so that everyone else would be able to verify. And if the computation of the next seed is correct, as verified by everyone, then the next seed will now be used by everyone when making next proposals. And when understanding whether the node is a member of the next committee. So a proof of the sortition hash is actually not included with gossip separately. These are probably secondary details. Now, Algorand is an interesting system. Because it's designed it includes very interesting ideas, the VRF, the sortition, selection of the committees to run the consensus, and so on. However, it also spurred a controversy. It evoked some controversy about what? About why. So one of the main questions about Algorand is how are the participants incentivized to make proposals? In Algorand, there are no fees. So why would the nodes be doing whatever they are supposed to do? Even the good nodes. So the assumption of Algorand is that, again, there is 2/3 of honest nodes, more than 2/3 of honest nodes. And the honest nodes, they are not rational by that assumption. They would be just doing whatever they are supposed to do, regardless of whether they have any gain out of it. So that's a strong assumption. There are other systems with more interesting, maybe more practical assumptions. It's called the bar model. Bar means Byzantine altruistic rational. There are 3 classes of nodes. Byzantine want to spoil everything. Altruistic follow the protocol regardless of the gain. Rational follow the protocol, but only if it's in their interest. So they're not trying to break the system, but they may deviate from the protocol if it benefits their behavior. So that's a more practical model compared to the one adopted in Algorand. So that was a significant subject of the debate in Algorand. And that concludes the third lecture on Bitcoin NG in Algorand.